Welcome to Lecture 14, in which our sole objective is to discuss exercise 420. And in fact, all we really want to do is to understand the solution to part A of exercise 420, because the other parts are trivial. So I will leave it to you to read this exercise for yourselves, and then we want to understand how to solve it. So our state C in this problem is equal to 1 over square root of 2, 0, 0, plus 1, 1. And the first cubit is going to be measured. So let's say basis for measurement of the first cubit and then basis for measurement of the second cubit. And our basis for the measurement of the first cubit is V1 orthogonal, and our basis for the measurement of the second cubit is V2 orthogonal, where V1 is equal to cosine theta 1, 0, plus sine theta 1, 1. V1 orthogonal is minus sine theta 1, 0, plus cosine theta 1, 1. And of course, if you take the inner product of those two vectors, it's easy to see that these vectors are indeed orthogonal to each other. Furthermore, each of these vectors is of unit length. So this basis right here, this basis, measurement basis for the first cubit, is indeed an orthonormal basis. And then, as you might guess, V2 is cosine theta 2, 0, plus sine theta 2, 1. And V2 orthogonal is minus sine theta 2, 0, plus cosine theta 2, 1. So now what we want to do is to express C in terms of these kets. Okay, so C again is equal to 1 over square root of 2, 0, 0, plus 1 over square root of 2, 1, 1. And so when we let's maybe write this in the following way. This is 0 using a notation that we used in one of our problems earlier. This is 0 for the first cubit and 0 for the second cubit, and this one is 1 for the first cubit and 1 for the second cubit. Now, since the first cubit is going to be measured with the basis V1 orthogonal, and the second cubit will be measured with the basis V2 orthogonal, we will express the 0 here for the first cubit and the 1 here for the first cubit in this term. We will express those in terms of V1 and V1 orthogonal, and this 0 sub 2 and 1 sub 2 will be expressed in terms of V2 and V2 orthogonal. Now, how is this done? Well, it's actually fairly straightforward. If we look at these expressions here for V1 orthogonal, V2, and V2 orthogonal, we will notice the following. I guess I'll just put it over here to the side. 0, if we look at V1 and V1 orthogonal, 0 we can see is equal to cosine theta 1 V1 minus sine theta 1 V1 orthogonal. You can clearly see this because if we multiply V1 times cosine theta 1 and V1 orthogonal by minus sine theta 1, and then add these two, and then add them together, we'll get cosine squared theta 1, 0, plus sine squared theta 1, 0. So we'll get 0, and then for the terms multiplying the 1 cat, we'll get cosine theta 1, sine theta 1, minus sine theta 1, cosine theta 1, so that will drop out. Similarly, if we want to write the 1 cat in terms of V1 and V1 orthogonal, we see that we should do here sine theta 1. Now, actually, this won't be needed, because notice that down here for the it will be needed right here. So go ahead and I'm going to put a 1 here just to stress that we're talking about the first cubit. Okay, so the 1 in the first cubit can be written as sine theta 1 V1 plus cosine theta 1 V1 orthogonal. And then in a very similar fashion, we conclude that 0 in the second cubit is equal to cosine theta 2 V2 minus sine theta 2 V2 orthogonal, and 1 in the second cubit is equal to sine theta 2 V2 plus cosine theta 2 V2 orthogonal. So when we take these expressions and use them to substitute down here, we will get the following: 1 over square root of 2, and then cosine theta 1 V1 minus sine theta 1 V1 orthogonal, and for 0, 2, we will have cosine theta 2 V2 minus sine theta 2 V2 orthogonal. And now we have to include the second term, 1 over square root of 2. Now we're doing this term. And so we have sine theta 1 V1 plus cosine theta 1 V1 orthogonal sine theta 2 V2 plus cosine theta 2 V2 orthogonal. And now if we put this all together, of course 1 over square root of 2 is common to all of those terms. And we'll get cosine theta 1, cosine theta 2, V1, V2, minus cosine theta 1, sine theta 2, V1, V2 orthogonal, minus sine theta 1, cosine theta 2, V1 orthogonal, V2, plus sine theta 1, sine theta 2, V1 orthogonal, V2 orthogonal. Those are all the terms we get from here. And now continuing with these terms, we will get plus sine theta 1, sine theta 2, V1, V2, plus sine theta 1, cosine theta 2, V1, V2 orthogonal, plus cosine theta 1, sine theta 2, V1 orthogonal, V2, plus cosine theta 1, cosine theta 2, V1 orthogonal, V2 orthogonal. And that's all the terms. And fortunately, this will simplify a good bit. The two terms with V1, V2, we have cosine theta 1, cosine theta 2 plus sine theta 1, sine theta 2. So that's the same thing as cosine of theta 1 minus theta 2, V1, V2. And then for the next term, we have sine theta 1 cosine theta 2 minus sine theta 2 cosine theta 1. So that's the sine of theta 1 minus theta 2, V1, V2 orthogonal. And now for the next term, we have sine theta 2 cosine theta 1 minus sine theta 1 cosine theta 2. So that's the sine of theta 2 minus theta 1, or minus the sine of theta 1 minus theta 2 times V1 orthogonal V2. And then finally, cosine plus sine again gives us cosine of theta 1 minus theta 2, V1 orthogonal, V2 orthogonal. And that is the result now of putting C, expressing it entirely in terms of V1 orthogonal, V2, and V2 orthogonal. And so what we see here is that the probability that the two measurements, now remember that V1 is associated with the V1 and V2 are associated with the eigenvalues of 1, and V1 orthogonal and V2 orthogonal are associated with the eigenvalues of -1. So the probability that both qubits will agree with each other, in other words, that both will correspond to the +1 eigenvalue or both will correspond to the -1 eigenvalue, is going to be this coefficient squared plus this coefficient squared, and then of course don't forget the 1 over square root of 2 out in front. So that so we'll say that the qubits we'll just say that the we'll put it in terms that the book has. We'll say that the measurements agree. But again, what that means is that by measurements agree, that means that either both measurements yield the eigenvector associated with the +1 eigenvalue, or that both yield eigenvector associated with the -1 eigenvalue. And the probability of that will be cosine squared of theta 1 minus theta 2 over 2. That's this first, taking into account, of course, the 1 over square root of 2 out front. That's the first coefficient squared. And then when we square the second coefficient, of course, we get the same thing, cosine squared of theta 1 minus theta 2 over 2, which, of course, just comes out to be cosine squared of theta 1 minus theta 2. And on the other hand, the probability that the measurements don't agree is equal to sine squared of theta 1 minus theta 2 over 2 plus sine squared theta 1 minus theta 2 over 2. And you see that's simply the other terms. We have V1, V2 orthogonal, so we have one associated with a +1 eigenvalue and one associated with a -1 eigenvalue, and here we have one with a -1 eigenvalue, one with a +1 eigenvalue. So in this case, the measurements are not agreeing, and so the probability that that happens is this over the square root of 2 squared plus this. And of course, when we square the negative sign, that goes away. So we have this, which of course is sine squared of theta 1 minus theta 2. And as expected, we see that these two probabilities add to 1. And now that we have this information, this can be used. This result actually is used in the explanation of the of Bell's inequality and the EPR paradox. So I believe that now you're prepared, or at least better prepared, to read that material right at the end of chapter 4 and understand what's going on there. So now I will do some problems, and these are more along the lines of review than being explicitly about the EPR paradox or Bell's theorem. So let's break for just a moment, and then we'll take a look at these problems. So now for the problems for this lecture. We're supposing that we measure the general 2-qubit state psi, which is equal to A times 0, 0 plus B times 0, 1 plus C times 1, 0 plus D times 1, 1, where A, B, C, and D are in general complex. We, for the first 3 questions, 14.1, 14.2, and 14.3, we assume that Alice measures the first qubit with the standard basis and Bob measures the second qubit with the standard basis. So the first question, 14.1, is what is the probability that Alice measures 0? And this is regardless of what Bob is doing. We just want to know the total probability that Alice measures 0. 14.2, what is the probability that Bob measures 1? And again, this is regardless of what Alice does. What is the total probability that Bob measures 1? Now in 14.3, we have a little bit different kind of question. If it is known that Alice has measured 0, what is the probability that Bob measures 1? Now, this is what some people would refer to as a conditional probability. What is the probability that Bob measures a 1 given that we already know that Alice has measured 0? And then finally, in 14.4, if both qubits of psi, and here instead of Alice measuring the first qubit and Bob measuring the second qubit, now we're assuming that both qubits are measured simultaneously using the bases 0, 0, 0, 1, 1, 0, and 1, 1. What is the probability of the outcome 0, 1? And here are your choices. So those are the problems for this lecture, and good luck.